Hello there, and welcome to Secretum Histories, where curiosity grows quiet, where science slows its pace, and where large ideas are allowed to soften rather than demand attention. Tonight we begin a gentle and careful exploration of something that has hovered at the edges of public imagination for decades, something often spoken about loudly, argued about fiercely, and yet rarely approached slowly. This is the idea of Nibiru, not as a myth shouted across comment sections, but as a shadow cast by data, silence, and the long patience of astronomy. This story is not about certainty or revelation. It is about how knowledge is gathered, filtered, delayed, and sometimes misunderstood when it comes from the farthest reaches of space. NASA is often imagined as a vault of secrets, a place where answers sit locked away behind classified doors. In reality, it is closer to a vast library in constant motion, filled with incomplete pages, provisional conclusions, and shelves marked under review. When people speak of what NASA knows about Nibiru, they are often reacting not to statements made but to statements avoided, to data released without commentary, to discoveries explained narrowly while leaving room for wider interpretation. This is where stories begin, not in deception, but in absence. Silence, after all, has a way of inviting voices to fill it. The idea of a hidden planetary body did not begin with ancient tablets or internet forums. It began with mathematics. Long before Nibiru became a name loaded with fear or fascination, astronomers noticed something subtle and deeply unexciting on the surface. The outer planets did not behave exactly as predicted. Their orbits showed small irregularities, tiny deviations that suggested gravitational influences not fully accounted for. This was not unusual. In fact, this same process had already led to the discovery of Neptune in the 19th century. An unseen object could announce itself without ever being directly observed, simply by the way it tugged on others. This method of discovery trained astronomers to take anomalies seriously but cautiously. Every unexplained motion could point to something new, or it could vanish with better measurements. As instruments improved, many early irregularities were resolved. Others lingered, resurfacing periodically as datasets grew larger and more precise. In these unresolved corners of orbital mechanics, the placeholder name Planet X emerged. It was not a prophecy or a conspiracy. It was a label, a way of saying something might be missing from the equation. NASA inherited this cautious language when it was formed. Its mandate was not to announce mysteries but to reduce them. And yet reduction takes time. The outer solar system is vast beyond everyday comprehension. Distances stretch so far that light itself takes hours to cross them. Objects move slowly, tracing arcs so long that a single human lifetime may not capture a full orbit. In such an environment, patience is not a virtue. It is a requirement. As telescopes evolved from optical to infrared, NASA's relationship with the unknown shifted. Infrared astronomy allowed scientists to see heat rather than light, to detect objects too cold and dark to reflect sunlight effectively. This was a turning point. Suddenly the solar system was no longer limited to what could be seen shining. It included what glowed faintly in the long wavelengths of residual warmth. Missions like IRAS, WISE, and later NEOWISE scanned the sky repeatedly, cataloguing millions of objects. Most were ordinary. Some were distant galaxies, some were brown dwarfs, some were near-Earth asteroids, and a small number resisted easy classification. NASA released these catalogues publicly. The data was accessible, downloadable, searchable. What it did not always provide was narrative. Raw data is silent. It does not explain itself. It waits for interpretation, and interpretation requires context, caution, and time. When members of the public or independent researchers noticed entries that seemed unusual, objects detected briefly and then lost, heat signatures without clear counterparts, or trajectories that defied simple categorization, stories began to grow. Not because NASA claimed anything, but because it did not immediately close every loop. Within NASA, ambiguity is not treated as drama. It is treated as work. Objects are flagged, reobserved, cross-checked against background noise and known phenomena. Many anomalies resolve into calibration errors, sensor artifacts, or known classes of objects behaving normally at extreme distances. Others remain provisional. They sit in databases marked with uncertainty, awaiting future passes, better instruments, or corroboration from independent observatories. This process can take years, sometimes decades. To the public, however, time moves differently. An unanswered question feels unfinished. An unfinished story feels suspicious. The name Nibiru entered this gap not through NASA documentation, but through the merging of ancient mythological language with modern astronomical anxiety. The term was retrofitted onto Planet X, despite the two originating in entirely different intellectual traditions. NASA never adopted the name, never used it internally, never referenced it in official communications, yet its silence on sensational interpretations was often interpreted as avoidance rather than restraint. NASA has, on multiple occasions, explicitly denied the existence of a rogue planet on a collision course with Earth. These statements were clear, firm, and public. What NASA did not do was engage deeply with every variation of the idea, every reinterpretation, every speculative leap connecting infrared surveys to catastrophic narratives. Institutions built on evidence do not argue with hypotheticals endlessly. They publish findings. They correct errors. They move forward. At the same time, NASA continued to fund and support research into the outer solar system. Kuiper belt objects were discovered in vast numbers. Distant trans-Neptunian objects exhibited clustering in their orbits that suggested a gravitational shepherd. This led to the modern hypothesis of Planet 9, a distant massive object far beyond Neptune, influencing orbital patterns without ever approaching the inner solar system. This idea came from peer-reviewed research, not secrecy. NASA acknowledged it, discussed it, and supported ongoing observation efforts. Here is where misunderstanding often takes root. Planet 9 is not Nibiru as popularly imagined. It is not a brown dwarf. It does not approach Earth. It does not follow an elongated path through the inner solar system. It is distant, cold, slow, and stable on timescales far exceeding human history. Yet for those already primed to expect concealment, any acknowledgement of an unseen massive object feels like confirmation of something withheld. NASA's communication style does not help this perception. It speaks in probabilities, confidence intervals, and provisional language. It avoids definitive claims until evidence is overwhelming. It updates quietly when data changes. To an audience accustomed to narrative closure, this feels unsatisfying. But it is precisely how science avoids error. What NASA knows about distant objects is always incomplete by design. Knowledge grows asymptotically, approaching clarity without ever fully reaching it. Each survey improves resolution but also reveals new questions. Each detection narrows uncertainty but rarely eliminates it entirely. The outer solar system remains one of the least mapped regions of our cosmic neighbourhood. This is not a failure. It is a frontier. As this story continues, it will move deeper into how data is gathered, why some discoveries take so long to confirm, and how modern astronomy balances openness with responsibility. There will be no sudden revelations here, no dramatic unveilings, only the slow accumulation of context, the quiet rhythm of observation, and the understanding that not everything unexplained is hidden, and not everything unseen is unknown. The idea of Nibiru persists because it sits at the intersection of curiosity and unease. It draws energy from gaps, from delays, from the natural human tendency to seek meaning in patterns not yet resolved. NASA operates within those same gaps, but with different tools and different obligations. Where imagination fills space with story, science fills it with measurement, returning again and again until what once felt mysterious becomes mundane. And yet, the mundane has a way of becoming fascinating when approached without urgency. The outer solar system is not empty. It is quiet. It moves slowly. It reveals itself only to those willing to wait, as attention drifts outward, away from headlines and toward long arcs and faint signals. The distinction between what is known, what is suspected, and what is imagined begins to sharpen. Not all at once, but gradually, in a way that mirrors the movement of the objects themselves. From here, the path leads backward before it leads forward, into the earliest moments when astronomers first suspected something unseen, long before the name Nibiru carried weight. That earlier history provides the foundation for everything that follows, grounding speculation in observation and separating inherited myth from measured uncertainty without needing to force a conclusion. Long before the word Nibiru carried weight, before it became wrapped in fear, fascination or speculation, the idea of a hidden world emerged quietly from mathematics, not myth. It did not arrive as a revelation nor as a warning. It appeared instead as a discrepancy, a small unease inside otherwise reliable equations. This is how many scientific ideas are born, not from bold declarations, but from numbers that refuse to settle into place. In the late 18th and early 19th centuries, astronomy was entering a period of increasing precision. Telescopes were improving, observational records were becoming more systematic, and celestial mechanics, guided by Newton's laws, offered a framework that seemed almost complete. Planetary motions could be calculated, predicted, and checked against observation with impressive accuracy. When predictions failed, even slightly, it was treated not as embarrassment, but as opportunity. Uranus was the first major trigger. Discovered in 1781, it was the first planet found with a telescope rather than naked eye observation. Once its orbit was charted, astronomers noticed something unsettling. Uranus did not move exactly as Newtonian mechanics said it should. The deviations were small but persistent. Over years, then decades, the mismatch remained. The simplest explanation was not that Newton was wrong, but that something unseen was exerting gravitational influence. Two mathematicians working independently proposed the same solution. There must be another planet beyond Uranus. They calculated where it should be, how massive it must be, and how it would pull on Uranus to create the observed irregularities. When astronomers pointed their telescopes to the predicted location, Neptune was found almost exactly where mathematics said it would be. This moment left a deep psychological imprint on astronomy. Invisible objects could announce themselves through gravity alone. The universe, it seemed, could hide things in plain sight. This success planted a seed. If one unseen planet had been discovered through orbital anomalies, why not another? As attention turned farther outward, astronomers began examining Neptune's own motion with similar scrutiny. Once again, small discrepancies appeared. They were subtler than those seen with Uranus, but enough to raise interest. Percival Lowell, an American astronomer known both for his dedication and his tendency toward overinterpretation, became convinced that another planet existed beyond Neptune. Lowell referred to this hypothetical object simply as Planet X. The name was not dramatic. It did not imply danger, intelligence, or intention. It meant unknown. Lowell spent years searching for it, building observatories, commissioning calculations, and directing sky surveys. His work did not produce Planet X as he envisioned it, but it did lead indirectly to the discovery of Pluto in 1930. Pluto, however, was not what Lowell had predicted. It was far too small to account for the gravitational effects he expected. For a time, Pluto was assumed to be more massive than it actually is, allowing it to serve as a convenient placeholder. Once its true size became clear, the original problem returned. If Pluto was too small, then what had caused the irregularities? As measurements improved, the anomalies that motivated Lowell began to dissolve. Better data corrected earlier assumptions. Some discrepancies vanished entirely. Others were revealed to be artifacts of incomplete measurements. Planet X faded into the background, not disproven, but no longer required. Science moved on, as it often does, without ceremony. But the idea did not disappear completely. It lingered quietly, resurfacing whenever new data hinted at something unexplained. Throughout the 20th century, astronomy expanded its reach, but the outer solar system remained difficult to study. Objects there were faint, slow-moving, and often indistinguishable from background stars without long-term observation. Gaps in knowledge persisted, not because of secrecy, but because of distance. NASA entered this story much later, inheriting both the tools and the unresolved questions of earlier astronomy. Its focus was not Planet X as a concept, but comprehensive mapping. Satellites, probes, and space-based telescopes extended observation beyond the limits of Earth's atmosphere. What they found was not a single missing planet, but a population. The Kuiper Belt, once hypothetical, was revealed as a vast region of icy bodies beyond Neptune. Hundreds became thousands, then tens of thousands. Their orbits were diverse, inclined, elongated, and sometimes extreme. Farther still, the Oort cloud was inferred, a distant spherical reservoir of cometary material extending nearly halfway to the nearest stars. The solar system was no longer neat and orderly. It was layered, textured, and crowded. As this complexity emerged, so did new patterns. Certain distant objects appeared to share unusual orbital alignments. Their paths clustered in ways that random chance struggled to explain. This did not immediately suggest a single, massive planet, but it reopened the old door. Gravity, once again, seemed to be whispering that something unseen might be shaping the architecture. At this stage, there were still no rumours. There were only papers, equations, simulations, and debates conducted in academic language. The public was largely unaware. NASA released data sets rather than narratives. The idea of a hidden world remained confined to technical discussions, where speculation was tempered by caution and evidence. The transition from scientific curiosity to public myth required something else. It required the merging of this restrained uncertainty with older symbolic language. The name Nibiru did not arise from astronomy. It came from reinterpretations of ancient Mesopotamian texts, filtered through modern anxieties and amplified by media ecosystems designed to reward attention rather than accuracy. Once the name attached itself to the idea of a hidden planet, everything changed. The concept was no longer neutral. It was no longer simply an object whose mass and orbit were unknown. It became intentional, cyclical, and dangerous. NASA, which had never used the name, now found itself responding to questions framed in unfamiliar terms. From NASA's perspective, the situation was unusual. The agency was being asked to explain or deny something it had never proposed. Its statements were straightforward. There was no evidence of a rogue planet entering the inner solar system. There was no hidden threat. Observations did not support catastrophic scenarios. These answers were accurate, but they did not satisfy those whose expectations were shaped by narrative rather than data. What NASA did not do, and what it rarely does, was issue sweeping explanations about why certain ideas gain traction. Institutions focused on observation are often ill-equipped to counter belief systems. They correct facts, they publish results, they move on. Silence in this context was not concealment, it was procedural. Meanwhile, the scientific exploration of the outer solar system continued. The idea of a distant massive object influencing orbital clustering resurfaced in a more refined form. This time, it was not Planet X reborn, but Planet 9, a hypothesis grounded in statistical analysis and numerical simulations. NASA acknowledged the research, discussed its implications, and supported observational efforts to confirm or refute it. Planet 9, however, existed only in the language of probability. It was a possible explanation, not a discovery. Its proposed orbit placed it far beyond Neptune, never approaching the inner solar system. Its timescale stretched over tens of thousands of years. There was no urgency, no threat, no drama. For those seeking cosmic significance, this was unsatisfying. The contrast between the slow pace of science and the rapid spread of speculation widened. Data was public, but interpretation fragmented. NASA's role became paradoxical. It was both the source of raw information and the target of accusations about withholding meaning. In truth, meaning was never something NASA claimed to possess fully. The earliest idea of a hidden world was never about secrecy. It was about humility. It acknowledged that even well-tested laws operate within limits set by observation. When observation improves, explanations change. Sometimes objects appear, sometimes they dissolve into noise. This is not failure, it is refinement. As this thread continues, attention will move from the early mathematical whispers to the modern instruments that listen for them. Understanding how NASA observes the dark outskirts of the solar system helps clarify why some ideas persist, why others fade, and why the absence of certainty is not the same as the presence of concealment. The story of hidden worlds has always been less about what is kept from view and more about how slowly the universe allows itself to be seen. By the time astronomers began to suspect that something might be missing beyond the known planets, the solar system had already been reduced, at least on paper, to something that looked orderly and predictable. Newton's laws had been tested again and again. Orbits could be calculated decades in advance. Eclipses arrived on schedule. Comets returned as expected. The sky, once feared and mythologized, had become a machine that could be modelled, trusted and relied upon. It was precisely this confidence that made the earliest anomalies so unsettling. The motions of the outer planets are slow. From Earth's perspective, they crawl across the background of stars with almost stubborn patience. Uranus takes 84 years to complete a single orbit. Neptune takes 165. A small error in observation can take decades to reveal itself, and a mistaken assumption can survive for an entire human lifetime before being corrected. This meant that early discrepancies were not dramatic deviations, but faint drifts, visible only when observations were stacked, averaged, and compared across generations. When Uranus was discovered, astronomers celebrated not just a new planet, but a triumph of method. Its orbit was calculated using the same equations that governed the motions of the others, and initially everything appeared to fit. Over time, however, the planet began to arrive slightly ahead of schedule, then slightly behind. The difference was small, barely noticeable in any single year, but unmistakable when decades were laid side by side. Something was nudging Uranus, and gravity was the only reasonable explanation. This realization did not inspire panic. It inspired calculation. If gravity was responsible, then the mass, distance, and position of the unseen object could be inferred mathematically. This was not guesswork. It was deduction. When Neptune was eventually found almost exactly where predicted, the success was so complete that it permanently reshaped how astronomers thought about absence. The invisible could be real. The unseen could be measured. Space could contain more than it revealed. Once Neptune joined the planetary family, attention naturally turned outward. If one missing planet had existed before, perhaps another waited farther still. Astronomers began examining Neptune's motion with the same scrutiny once applied to Uranus. Here, however, the situation became more complicated. The anomalies were less consistent. Some data sets suggested irregularities, others did not. The farther the planet, the harder it was to isolate true gravitational effects from observational uncertainty. At this stage, the phrase Planet X entered astronomical vocabulary. It was not a declaration, it was a placeholder. a symbol used in equations to represent an unknown mass whose properties had not yet been established. Planet X did not have a story. It did not have an orbit. It was simply a term that allowed calculations to continue without prematurely closing the question. Percival Lowell became the most visible advocate of this idea. He was convinced that Neptune's motion still carried the signature of an unseen companion. Lowell invested enormous resources into the search, commissioning calculations and photographic surveys. His confidence was unshaken, but confidence is not evidence, and astronomy does not reward persistence alone. The discovery of Pluto seemed at first to vindicate Lowell's efforts. A new object had been found beyond Neptune. The timing felt appropriate, the narrative fit neatly. Yet Pluto immediately presented problems. It was too small. Its mass, once properly measured, was insufficient to explain the gravitational effects Lowell had predicted. The planet that wasn't there had been replaced by a planet that could not do the job assigned to it. For several decades, this inconsistency was tolerated rather than resolved. Pluto's mass was overestimated. Models were adjusted. The idea of Planet X remained quietly alive, sustained not by new evidence, but by unresolved assumptions. It was only when measurements improved significantly that the situation clarified. Pluto was far too light. The original anomalies attributed to Neptune's motion were largely the result of incomplete data. Once this became clear, something interesting happened. The problem did not explode. It evaporated. Improved observations removed the need for Planet X entirely. Neptune's orbit, when recalculated using more accurate values for planetary masses, aligned with predictions. The ghost disappeared not because it had been chased away, but because it had never truly been there. This moment is rarely emphasized outside of academic histories, yet it is crucial. The absence of Planet X was not a cover-up. It was a correction. Science did what it is designed to do. It revised itself quietly and moved forward. No announcement was required. No apology was necessary. The universe had not changed. Only understanding had. However, the idea left a residue. The success of Neptune's prediction had taught astronomers that unseen objects could exist. The failure of Planet X taught them something equally important. Not every anomaly points to a new world. Some are artifacts of measurement. Some dissolve with better tools. The challenge lies in distinguishing between the two, especially when dealing with distances so great that direct observation borders on the impossible. As the 20th century progressed, attention shifted away from individual planets and toward populations. Astronomers began to realize that the outer solar system was not sparsely populated, but crowded with small bodies. The Kuiper Belt, once theoretical, emerged as a vast region of icy debris beyond Neptune. Its discovery reframed earlier questions. Irregular motions might not require a single massive planet. They could result from the combined gravitational effects of many smaller objects. This realization complicated the narrative. Instead of searching for one missing planet, astronomers now had to account for thousands of distant bodies, each contributing minuscule influences. Modelling such a system is computationally demanding. Small errors compound, assumptions multiply. The farther outward one looks, the more the solar system resembles a dynamic ecosystem, rather than a tidy clockwork. NASA entered this landscape as an observer and organizer rather than a storyteller. Its role was to gather data, catalogue objects, and refine measurements. Missions like Voyager provided glimpses of the outer planets, but they were brief flybys. The long-term behaviour of these regions required surveys, not visits. Space-based telescopes expanded reach, but even they faced limitations. Early infrared surveys detected faint heat signatures in the outer solar system. Some corresponded to known objects, others did not. Many detections were transient, appearing once and then vanishing below detection thresholds. This was not unusual. Noise, background sources, and instrumental artifacts all produce false positives. Each candidate had to be examined, reobserved, and either confirmed or discarded. From the inside, this process was methodical and unremarkable. From the outside, it looked like uncertainty. Lists of unidentified objects circulated. Amateur analysts downloaded datasets and noticed gaps, inconsistencies, or entries that seemed unresolved. Without the context of error margins and calibration limits, these details took on significance they did not possess in isolation. NASA's position remained consistent. There was no evidence of a massive planet moving through the inner solar system. There was no undisclosed object on a collision course. The outer solar system was still being mapped. These statements were accurate, but they did not address the deeper discomfort some people felt. If anomalies existed before and led to Neptune, why should new anomalies not lead to something similar now? The answer lies in scale and sensitivity. The anomalies that led to Neptune were large enough to stand above noise. They were consistent across observers and instruments. The early anomalies attributed to Planet X were smaller and ultimately explained. Modern anomalies often exist at the edge of detection, where signal and noise intertwine. Distinguishing between them requires patience rather than proclamation. The phrase, "the planet that wasn't there," captures this dynamic precisely. It acknowledges that absence can feel as significant as presence when expectations are strong. The human mind prefers completion. An unanswered question invites speculation. A delayed resolution invites suspicion. Science, however, operates comfortably within delay. As data quality improved, attention shifted once again. This time, not to Neptune's orbit itself, but to the orbits of distant Kuiper Belt objects. Certain extreme objects exhibited clustering that resisted random explanation. This pattern revived the idea of a distant massive influencer, not because of planetary motion, but because of the distribution of smaller bodies. The narrative returned, but in a new form. Unlike Planet X, this idea was carefully constrained. The hypothetical object would be far away. Its orbit would be long and stable. It would not enter the inner solar system. It would not repeat the mistakes of earlier assumptions. It was, in effect, an attempt to learn from the planet that wasn't there. Throughout this entire history, NASA's knowledge remained incremental. There was never a moment when an unseen planet was discovered and hidden. There were moments when anomalies appeared, were investigated, and were either resolved or recontextualized. The absence of drama was not evidence of concealment. It was evidence of process. Understanding this helps dissolve the illusion of a singular missing world lurking just beyond detection. The outer solar system is not hiding one secret. It is revealing many small ones slowly. Some will turn into discoveries. Others will vanish under better measurement. This is not a flaw. It is the rhythm of observation. As the focus moves forward, attention will settle on how modern instruments watch the darkness and why their silence is often misinterpreted. The story of early anomalies is not a prelude to revelation, but a lesson in restraint. It shows how easily expectation can outpace evidence, and how often the most important discoveries arrive not as confirmations of rumour, but as quiet corrections that leave no mystery behind, only clarity waiting to be recognised. The shift from Planet X to Nibiru did not happen inside an observatory, and it did not originate in any scientific journal. It happened gradually, in the space between technical language and human storytelling, where caution sounds like evasion and uncertainty feels unfinished. Planet X was never meant to be a character. It was a variable, a stand-in for something not yet known, a temporary marker used to keep equations open rather than conclusions closed. Nibiru, by contrast, became a narrative, and narratives behave very differently from hypotheses. Planet X existed comfortably within science because it carried no expectations beyond explanation. It did not promise arrival. It did not suggest intention. It did not imply consequence. It simply acknowledged that, given the data at the time, something might be missing. When the data improved and the need vanished, Planet X faded without resistance. That is the fate of most placeholders in science. They do their job and disappear. The transformation began when the idea of an unseen planet escaped the slow environment of peer review and entered the faster currents of popular interpretation. At that point, the placeholder lost its boundaries. It became detached from the specific anomalies that had once justified it, and free to absorb meaning from elsewhere. This is where ancient language entered the picture, not as history, but as reinterpretation. The name Nibiru originates from Mesopotamian texts, where it referred to a point of crossing, sometimes associated with celestial movement, sometimes with divine order, and sometimes with ritual symbolism. It was not a planet in the modern sense. It was not an object with mass, orbit, or gravitational influence. It was a concept, flexible and contextual, interpreted differently across texts and eras. It belonged to mythology and cosmology, not astronomy. The leap from symbolic reference to physical body occurred much later, driven by modern expectations that ancient cultures possessed hidden scientific knowledge encoded in metaphor. This idea is appealing because it suggests continuity, that the past knew something the present has forgotten, and that rediscovery is inevitable. In this framework, Planet X became the scientific echo of Nibiru, and Nibiru became the ancient name for Planet X. The fact that these ideas arose independently, in entirely different intellectual traditions, was treated not as a problem, but as proof. NASA found itself drawn into this convergence without participating in it. The agency never linked Planet X to ancient mythology. It never adopted the name Nibiru. It never framed its research in symbolic terms. Yet because NASA was the most visible authority on space, it became the focal point for interpretations that blended science and myth into a single narrative. What accelerated this process was the emergence of the internet as a primary source of information. Data that once circulated mainly among specialists became publicly accessible, but without the scaffolding of expertise that gives it meaning. Infrared surveys, orbital catalogues, and lists of unidentified objects were downloaded and examined by individuals outside the institutional context in which they were produced. This was not inherently problematic. Curiosity is not a threat to science. Interpretation without constraint, however, can be. When members of the public encountered entries marked as uncertain, provisional, or unresolved, they often assumed that uncertainty implied significance. An object not fully explained became an object deliberately unexplained. A detection not immediately followed up became a detection intentionally ignored. In this environment, Planet X did not need to exist physically to feel real. It existed narratively, sustained by gaps that science treats as normal and storytelling treats as suspicious. Nibiru entered as a solution to narrative discomfort. It provided a name, a history, and a sense of purpose. It transformed a technical possibility into a cosmic actor. Once named, it could be imagined. Once imagined, it could be feared. And once feared, it could be expected. The absence of confirmation then became part of the story rather than a challenge to it. NASA's responses during this period were consistent and restrained. The agency clarified repeatedly that there was no evidence of a large object on a dangerous trajectory toward Earth. It explained how surveys worked, how infrared detection could be misinterpreted, and why certain objects appeared briefly and then vanished from catalogues. These explanations were factual, but they lacked the emotional resonance of the narratives they were countering. Science communicates by reduction. Myth communicates by expansion. When NASA said there was no evidence, it meant the hypothesis failed under scrutiny. When believers heard no evidence, they heard no admission. The same words travelled different cognitive paths. The idea of Nibiru gained additional strength from timing. It flourished during periods of cultural anxiety, when distrust in institutions was already high and apocalyptic thinking found receptive ground. Planetary alignments, calendar cycles, and global events were woven into the narrative, giving it urgency. Predictions of arrival dates appeared, passed, and were revised. Each failure did not weaken belief. It reinforced the idea that something had intervened, that concealment had intensified. NASA did not adapt its communication strategy to this evolving myth. It continued to operate within its own framework, where failed predictions discredit hypotheses rather than renew them. This mismatch allowed the narrative to persist alongside official denial without direct confrontation. Silence was interpreted as discomfort. Repetition was interpreted as deflection. Meanwhile, genuine scientific developments continued. The discovery of thousands of Kuiper Belt objects reshaped understanding of the outer solar system. The identification of extreme trans-Neptunian objects revealed patterns that demanded explanation. These findings led to the Planet 9 hypothesis, which was careful, limited, and explicitly non-catastrophic. NASA acknowledged this work openly, supported observational efforts, and emphasized uncertainty. To those invested in the Nibiru narrative, Planet 9 appeared as confirmation wearing a different name. The distinctions mattered scientifically, but not symbolically. Both involved unseen objects beyond Neptune. Both relied on gravitational inference. The differences in orbit, mass, and behavior were treated as technicalities rather than disqualifiers. This conflation illustrates how a scientific placeholder becomes a myth not through deception, but through translation. Planet X was translated out of its context. Nibiru was translated into one. The result was a hybrid idea that satisfied emotional and narrative needs, while resisting empirical resolution. NASA's knowledge did not change during this transformation. What changed was the audience. The same data was read differently depending on expectation. For scientists, uncertainty narrowed with each survey. For mythmakers, uncertainty expanded with each unanswered question. The divergence widened. It is important to note that NASA does not suppress discoveries to manage public reaction. The history of astronomy shows the opposite. When new objects are found, they are announced quickly, often before their full implications are understood. Pluto, Eris, Sedna, and countless smaller bodies were introduced publicly without delay. The idea that a planet-sized object could be hidden in plain sight contradicts the incentives and culture of modern astronomy. Yet the myth persists because it does not rely on concealment alone. It relies on the feeling that something important is missing. The outer solar system remains largely unexplored compared to the inner regions. Maps are incomplete. Orbits are uncertain. This openness invites projection. Where science sees frontier, myth sees secrecy. NASA's refusal to adopt the language of myth has often been framed as avoidance. In reality, it reflects institutional discipline. Naming carries implication. To name something is to accept its premise. By not using the name Nibiru, NASA avoids legitimizing a framework that merges unrelated domains. This choice is not defensive, it is methodological. As Planet X faded and Nibiru rose, the core issue remained unchanged. How does one communicate provisional knowledge in a world that prefers definitive answers? How does one explain that not knowing yet is different from hiding forever? NASA's approach has been to continue observing, continue publishing, and allow time to resolve what speculation accelerates. The myth did not grow because NASA failed to explain. It grew because explanation alone cannot compete with meaning. Nibiru offers purpose. It suggests cycles, warnings, and relevance. Planet X offered none of these. It was content to exist or not exist without consequence. Understanding this transition helps clarify why debates around Nibiru persist despite repeated scientific dismissal. The argument is not about evidence. It is about narrative ownership. Science answers questions. Myths answer feelings. When the two intersect, confusion follows. As attention moves forward, the focus shifts to what NASA actually observes today, how modern surveys differ from earlier efforts, and why the language of caution remains central to interpretation. The story continues not because something has been hidden, but because the distance between what is known and what is desired has not yet closed. When people imagine NASA searching the far edges of the solar system, the picture is often cinematic. A single powerful telescope aimed into darkness, tracking one ominous object, waiting for it to reveal itself. The reality is quieter, slower, and far more procedural. NASA does not watch the distant dark for one thing. It watches everything it can, systematically, repeatedly, and without narrative preference. The programs involved are not secret hunts. They're broad surveys designed to reduce ignorance, not confirm expectation. At the core of NASA's observational strategy is coverage rather than focus. The outer solar system is not scanned the way one searches for a missing person. It is mapped the way one surveys an ocean. Large regions are observed repeatedly over long periods of time, using different wavelengths, instruments, and methods. The goal is not discovery alone, but context. An object means little unless it can be placed within a population, its motion tracked, its properties compared to others. One of the most important distinctions often overlooked is the difference between targeted observation and survey science. Targeted observation begins with a specific object in mind. Survey science begins with none. NASA's programs that explore the distant solar system overwhelmingly belong to the second category. They are designed to find whatever is there, not whatever is suspected. Infrared astronomy plays a central role in this effort. Objects in the outer solar system reflect very little sunlight. Many are coated in dark organic material, absorbing more light than they scatter. Optical telescopes struggle with such targets, especially at great distances. Infrared instruments, by contrast, detect heat. Even cold objects emit a faint thermal signature, and this emission does not depend on reflected sunlight. NASA's infrared astronomical satellite, launched in 1983, was an early attempt to survey the entire sky in infrared wavelengths. Its mission was not focused on planets at all. It catalogued stars, galaxies, dust clouds, and everything else that emitted infrared radiation. In doing so, it provided the first comprehensive infrared map of the sky. Among its detections were many objects that had no obvious optical counterpart. Most were distant galaxies, some were brown dwarfs, a few remained ambiguous. Ambiguity is not unusual in survey data. An initial detection is only a data point. It becomes meaningful only when confirmed by additional observations. NASA's later missions improved on this approach. The Wide Field Infrared Survey Explorer, known as WISE, launched in 2009, scanned the entire sky multiple times with far greater sensitivity. Its successor missions extended this work, focusing particularly on near-Earth objects, but continuing to collect data on the distant background. WISE did not look for Nibiru. It did not look for Planet X. It looked for everything. Its detectors recorded millions of sources, each logged with position, brightness, and movement. Objects that moved between scans were flagged as potential solar system bodies. Those that remained fixed were assumed to be distant stars or galaxies. Movement is the key signature of proximity. The challenge lies in scale. At extreme distances, even large objects move very slowly against the stellar background. Detecting motion requires patience and repetition. A planet far beyond Neptune might shift only a fraction of an arcsecond over months or years. Distinguishing such movement from noise demands precise calibration and long-term tracking. NASA's programs are structured around this reality. Surveys are repeated not to catch dramatic motion, but to accumulate subtle change. Data from different epochs is compared. Algorithms search for consistent patterns. Candidates are flagged, re-examined, and either confirmed or rejected. This process generates lists of objects in various stages of verification. Many misunderstandings arise at this stage. A candidate object is not a discovery, it is a possibility. Most candidates do not survive scrutiny. They fade as additional data clarifies their nature. This is not evidence of suppression, it is evidence of filtration. NASA publishes these catalogues openly. They include uncertainty estimates, confidence levels, and notes about data quality. To those unfamiliar with observational astronomy, these annotations can look like evasiveness. In reality, they are the opposite. They are disclosures of limitation. Beyond infrared surveys, NASA relies on optical telescopes, both space-based and ground-based, to refine observations. Objects detected in infrared are often followed up optically to determine orbit, composition, and size. This cross-wavelength approach reduces false positives. It also slows the process. Scheduling telescope time, coordinating international observatories, and waiting for favourable viewing conditions all introduce delay. Delay, however, is not inactivity. While the public sees silence, astronomers see workflow. Data moves from detection to analysis to modelling. Hypotheses are tested against simulation. Orbits are projected forward and backward. If an object cannot be reliably tracked, it does not become part of the accepted inventory. NASA also collaborates extensively with other institutions. The outer solar system is too vast for any single agency to monitor alone. European, Japanese, and private observatories contribute data. Amateur astronomers play a role as well, particularly in follow-up observation. The network is distributed, not centralized. This distribution makes the idea of concealment impractical. Discoveries are rarely owned by one institution. Data is shared. Results are replicated. Claims are scrutinized by independent groups with no incentive to protect NASA's reputation. A hidden planet would require coordinated silence across competing organizations, nations, and individuals. The structure of modern astronomy does not support such uniformity. Another important component of NASA's monitoring efforts involves dynamical studies rather than direct detection. Some objects are inferred not by seeing them, but by observing their effects. This approach relies on large data sets of small bodies, particularly those in the Kuiper Belt and beyond. Their orbits act as tracers of gravitational influence. Programs dedicated to cataloguing trans-Neptunian objects have revealed patterns that sparked renewed interest in distant massive bodies. Certain objects exhibit clustered orbital orientations that appear statistically unlikely under random distribution. This observation led to the Planet 9 hypothesis. It did not emerge from secrecy, but from publicly available data analysed by independent researchers. NASA's response to this hypothesis was measured. It did not declare a discovery. It acknowledged the plausibility of the explanation and supported continued observation. It emphasized uncertainty and alternative explanations. This restraint is often misread as avoidance. In reality, it reflects the difference between suggestion and confirmation. Planet 9, if it exists, would be extremely difficult to observe directly. Its distance would place it far beyond the reach of most current instruments. Its temperature would be low, its reflected light faint. Locating it would require deep surveys focused on specific regions of the sky identified through modelling. Such efforts are underway, but they are incremental. NASA's role here is supportive rather than directive. It funds surveys. It provides infrastructure. It does not dictate outcomes. If Planet 9 is found, it will be announced. If it is not, the hypothesis will be revised or abandoned. This outcome-neutral stance is central to scientific credibility. The distant dark is also watched indirectly through cometary behaviour. Long-period comets originate from regions far beyond the Kuiper Belt. Their trajectories carry information about gravitational perturbations in the outer solar system. By modelling comet influx patterns, astronomers can infer the structure of distant reservoirs like the Oort cloud. NASA's tracking of comets contributes to this understanding. Sudden increases or directional clustering can suggest external influences. So far, these patterns align with existing models of galactic tides and stellar encounters, rather than undiscovered planets passing through the inner solar system. Space probes have also contributed context. Voyager 1 and 2, while not designed to search for planets, provided invaluable data about the outer heliosphere. Their measurements of charged particles, magnetic fields, and plasma interactions help define the boundary between solar influence and interstellar space. This information constrains models of mass distribution in the outer system. What emerges from all these efforts is not a picture of a single hidden world waiting to be revealed, but a layered understanding of a complex region. The distant dark is populated, structured, and dynamic. It does not revolve around one object. It evolves under many influences. NASA watches this region continuously, but watching does not imply anticipation. The agency does not wait for confirmation of a particular idea. It waits for data to converge. When convergence happens, conclusions follow. When it does not, patience remains. The persistence of Nibiru as a concept often stems from misunderstanding this patience. The absence of announcement is taken as evidence of suppression rather than of non-confirmation. The steady release of data is taken as distraction rather than transparency. These interpretations say more about expectation than about practice. NASA's programs are designed to reduce uncertainty, not eliminate it entirely. Some uncertainty is irreducible at current technological limits. The outer solar system will remain partially unexplored for generations. This is not because something is being hidden, but because distance imposes cost. The real programs watching the distant dark are not dramatic. They do not operate in secrecy. They do not frame their work in terms of threat or revelation. They catalogue, compare, and correct. They build maps slowly, knowing that completeness is asymptotic. Understanding this helps reframe what NASA knows and what it does not claim to know. Knowledge is provisional. Observation is ongoing. Silence is not absence of effort. It is the sound of process continuing without narrative embellishment. As attention continues outward, the tools become more sensitive, the surveys more precise, and the questions narrower. The dark does not yield to curiosity all at once. It yields in fragments, each one reducing speculation by a small amount. What remains unexplained is not protected by secrecy, but by scale. From here, the focus moves toward how these observations are interpreted, why certain findings are discussed cautiously, and how the language of denial differs from the language of uncertainty. The distinction matters, because it is in that space that speculation either dissolves or hardens, depending on how patiently the data is allowed to speak. Human eyes are tuned for a very narrow slice of reality. We see the world in a thin band of light, a small window between infrared and ultraviolet that evolution selected not because it reveals truth, but because it is useful for survival. Beyond that window, the universe continues quietly, emitting signals our senses were never meant to register. When NASA looks into the distant reaches of the solar system, it does so by stepping outside human vision entirely, relying on instruments that perceive heat rather than brightness, motion rather than shape, and absence rather than form. Infrared astronomy is often misunderstood because it contradicts intuition. In everyday experience, darkness implies cold and emptiness. In infrared observation, darkness can glow faintly, and emptiness can hum with residual warmth. Every object with a temperature above absolute zero emits infrared radiation. That includes planets, asteroids, dust clouds, and objects so distant and dim that they reflect almost no sunlight at all. For regions like the outer solar system, where reflected light is scarce, infrared is not an enhancement. It is the primary sense. NASA's use of infrared telescopes did not begin as a search for hidden planets. It began as an attempt to see what optical instruments could not. Earth's atmosphere absorbs much of the infrared spectrum, making ground-based observation incomplete and distorted. To truly map infrared emissions, telescopes had to leave the planet entirely. This necessity shaped the design of missions that would later become central to discussions about what NASA can and cannot see. When the infrared astronomical satellite launched in the early 1980s, it carried modest expectations. Its detectors were primitive by modern standards. Its lifespan was short. yet it transformed astronomy by revealing a sky crowded with infrared sources. Many of these objects were invisible in optical wavelengths. Star-forming regions glowed. Dust clouds revealed structure. Entire populations of faint objects emerged where none had been catalogued before. Among these detections were sources that did not immediately resolve into known categories. Some appeared briefly, detected once or twice, then vanished into the noise. Others lacked clear optical counterparts. This was not alarming to astronomers. Survey data is full of such artifacts. Detectors are sensitive. Background radiation fluctuates. Cosmic rays strike sensors. Calibration errors occur. The vast majority of ambiguous detections are explained through follow-up observation or dismissed when they fail to repeat. What is important is that infrared surveys are not selective. They do not privilege one type of object over another. They sweep large areas of sky methodically, recording whatever emits at the wavelengths they are designed to detect. The result is not a curated list of discoveries, but an overwhelming flood of information. Making sense of it requires filtering, modelling, and time. NASA's later infrared missions expanded this approach dramatically. The Wide-Field Infrared Survey Explorer scanned the entire sky multiple times, with far greater sensitivity and resolution. Its mission architecture was built around repetition. By observing the same regions again and again, WISE could distinguish stationary background sources from moving foreground objects. Motion, even slight motion, is the signature of proximity. This method is powerful but slow. Objects in the distant solar system move at glacial speeds relative to the stellar background. A planet far beyond Neptune might take months to shift by an amount barely detectable. Detecting such motion requires not only precise instruments, but patience. Data must be compared across long baselines. Algorithms must separate genuine movement from instrumental drift. NASA's infrared surveys generate catalogues that reflect this provisional state. Entries are marked with confidence levels. Some are flagged as candidates. Others are identified as likely artifacts. These catalogues are not final statements. They are working documents. They exist to guide follow-up, not to declare discovery. To someone outside astronomy, this provisional language can appear evasive. Objects appear and disappear from lists. Classifications change. What was once ambiguous becomes mundane. This is not revisionism. It is refinement. Infrared detection alone rarely tells the full story. Heat signatures must be correlated with optical data, parallax measurements, and orbital modelling to confirm the nature of an object. NASA does not hide these uncertainties. It publishes them. The problem arises when provisional data is treated as suppressed knowledge rather than incomplete information. Infrared telescopes see things humans cannot, but they do not see meaning. Meaning is assigned later, through analysis. One persistent misunderstanding concerns the detection of brown dwarfs. These objects sit in the mass range between planets and stars. They emit infrared radiation but very little visible light. Early infrared surveys detected numerous brown dwarfs, some relatively close to the solar system. Their discovery fueled speculation that similar objects could exist farther out, perhaps even bound to the Sun. NASA acknowledged these findings openly. Brown dwarfs are now a well-established population. What NASA also made clear was that extensive surveys had ruled out nearby stellar mass or brown dwarf companions to the Sun. Objects of that size and temperature would have been detected easily by infrared instruments. Their absence is not assumed, it is measured. This distinction is often lost in translation. The fact that infrared telescopes detect many unseen objects leads to the assumption that anything unseen could be there. In reality, detection thresholds are well understood. Infrared surveys are exceptionally good at ruling out certain possibilities. They narrow the field even when they do not confirm specific objects. Another source of confusion involves transient detections. Infrared instruments sometimes register a signal that appears only once. These events are logged, flagged, and examined. Most are traced to noise, cosmic rays, or background fluctuations. A few remain unexplained but unrepeatable. In science, unrepeatable phenomena do not accumulate significance. They remain curiosities, not evidence. NASA does not elevate these curiosities into hypotheses unless they persist. Persistence is the currency of discovery. An object that cannot be tracked cannot be characterized. An object that cannot be characterized cannot be placed within a model. Infrared eyes are sensitive, but they are not omniscient. The silent nature of these surveys contributes to misunderstanding. Infrared telescopes do not produce dramatic images. Their data is numerical, abstract, and often visually unintuitive. Heat maps, spectral graphs, and motion plots do not lend themselves to storytelling. They require explanation, context, and patience. NASA's communication strategy has traditionally prioritized accuracy over accessibility. Technical results are released through papers and databases. Press releases focus on confirmed findings. Intermediate uncertainty remains largely undocumented in public-facing narratives. This creates a vacuum where speculation thrives. When people ask what NASA sees that we cannot, the answer is not a secret world lurking just beyond vision. It is a statistical landscape. Infrared telescopes see distributions, populations, gradients. They see absence as clearly as presence. They allow scientists to say not only what might be there, but what is almost certainly not. In the context of Nibiru, this matters deeply. A massive object moving through the inner solar system would emit infrared radiation detectable across multiple surveys. Its motion would be unmistakable. Its gravitational influence would distort known orbits measurably. Infrared eyes have not seen this, not because it is hidden, but because it is not there. What infrared telescopes do see is a distant, cold and complex region filled with small bodies. The Kuiper belt extends far beyond Neptune. Objects there vary widely in size, composition, and orbit. Some follow predictable paths. Others are tilted, elongated, or extreme. This diversity is real and observed. Farther still lies the inferred Oort cloud, too distant and diffuse to be observed directly. Its existence is deduced from cometary behaviour rather than direct detection. Infrared telescopes cannot image it as a structure. They can only constrain its properties indirectly. This limitation is often mistaken for ignorance. In reality, it reflects the boundary of current capability. NASA's infrared missions are complemented by future observatories designed to push these boundaries further. Each new instrument extends sensitivity slightly, expands coverage marginally, and refines models incrementally. No single telescope is expected to resolve every question. Progress is cumulative. The silence of these surveys is procedural, not conspiratorial. Data accumulates quietly. Analysis proceeds methodically. Discoveries are announced when confidence justifies them. The absence of dramatic revelation is not evidence of withholding. It is evidence that the universe does not conform to human pacing. Infrared eyes have transformed understanding of the cosmos precisely because they operate beyond intuition. They reveal that what seems empty is often full, and what seems mysterious is often mundane once enough data is gathered. They also reveal that some questions resist immediate answer, not because of secrecy, but because of scale. What space telescopes see that we cannot is not a hidden narrative, but a deeper version of the same one. A solar system shaped by gravity, populated by countless objects, evolving slowly over immense timescales. Infrared observation strips away illusion. It replaces speculation with constraint. As attention moves forward, the focus will shift from what is detected to how detection is interpreted and why certain explanations are favoured over others. The instruments provide signals. Humans provide stories. The distance between the two determines whether uncertainty becomes curiosity or suspicion. The infrared view does not whisper secrets. It offers limits, and within those limits, it steadily narrows the space where myth can comfortably reside. At the farthest margins of the solar system, where sunlight weakens into a pale suggestion and orbital periods stretch beyond recorded history, data behaves differently. It does not arrive cleanly. It does not repeat on convenient schedules. It accumulates slowly, often reluctantly, and sometimes in ways that resist immediate interpretation. It is here, in this thin boundary between detection and inference, that certain objects began to behave in ways that did not quite fit established expectations. These were not dramatic anomalies. Nothing arrived suddenly. No single observation forced a re-evaluation of everything that came before. Instead, patterns emerged gradually as catalogues grew and statistical confidence sharpened. Individual objects appeared unremarkable in isolation. It was only when compared against one another, when plotted together across long timescales, that something subtle began to take shape. The first hints came from extreme trans-Neptunian objects, bodies whose orbits carried them far beyond the Kuiper belt. These objects followed paths that were unusually elongated, tilted, or distant. None of this was inherently strange. The outer solar system is known for orbital diversity. Gravitational interactions with Neptune, stellar flybys, and the galactic tide all contribute to complexity. What caught attention was not that these objects were extreme, but that they were extreme in similar ways. Their orbital orientations showed a tendency to cluster. Perihelia pointed in roughly the same direction. Orbital planes were tilted in related angles. Under random distribution, such alignment would be unlikely, especially across objects discovered independently at different times. The clustering was not perfect. It did not form a rigid pattern. But it was persistent enough to resist dismissal as coincidence. This was not the first time clustering had been proposed. Earlier claims had been undermined by discovery bias. Telescopes do not observe the sky evenly. Surveys focus on certain regions more than others. Objects are easier to detect when they pass closer to the sun. These biases can create artificial patterns that disappear when corrected properly. Astronomers are acutely aware of this, and skepticism is the default response. What made this situation different was repetition across datasets. As more extreme objects were discovered, the alignment remained. Simulations were run to test whether observational bias alone could produce the effect. Some bias was present, but not enough to account for the full pattern. Something else appeared to be shaping these orbits. At this point, the language of science remained cautious. The phrase "does not quite fit" is as far as most conclusions went. The data suggested influence, not identity. Influence implies gravity, but gravity does not demand a single source. Multiple explanations remained viable. Perhaps the clustering was temporary, a transient configuration that would dissolve as more objects were found. Perhaps interactions within the Kuiper belt were stronger than previously modelled. Perhaps past stellar encounters had left a lingering imprint. NASA did not elevate these findings into declarations. The agency supported analysis, funded modelling, and released data. It did not frame the observations as evidence of a hidden planet. That framing came later, from interpretation rather than detection. Independent researchers proposed that a distant massive object could account for the observed clustering. This object would not resemble earlier conceptions of Planet X. It would not sweep through the inner solar system. Its orbit would be wide, inclined, and stable. Its influence would be subtle but persistent, shepherding smaller bodies over millions of years. This proposal was not sensational. It was constrained by mathematics. The object's mass was estimated within limits. Its distance was bounded by observational constraints. Its orbit was modelled rather than guessed. The hypothesis gained attention not because it was dramatic, but because it worked better than alternatives under current assumptions. NASA acknowledged the work without endorsing certainty. It emphasized that the hypothesis was provisional. Other explanations were still being tested. The dataset was small. More objects needed to be discovered before confidence could increase. This response reflected standard practice, but it did little to quiet speculation outside scientific circles. For those inclined toward narrative, the existence of objects that behaved strangely was enough. Behavior implies cause. Cause implies agency. Agency invites story. The gap between data and explanation became fertile ground for reinterpretation. It is important to understand how fragile these patterns are. A handful of new discoveries can weaken or strengthen statistical significance dramatically. One object discovered in an unexpected orientation can disrupt clustering entirely. This sensitivity is why astronomers hesitate to draw firm conclusions early. The outer solar system does not reveal itself quickly. Its geometry unfolds over time. NASA's role in this process is observational, not interpretive. The agency provides instruments, infrastructure, and access. Interpretation emerges from the community through debate and refinement. When NASA communicates about these findings, it does so with an emphasis on uncertainty. This emphasis is often misunderstood as reluctance to explain. The phrase, "objects that behave strangely," does not imply defiance of physics. It implies that existing models were incomplete. In science, this is expected. Models are tools, not truths. When data resists them, the models change. Some of the most discussed objects in this category are those with perihelia far beyond Neptune's influence. These objects should, under simple models, have been scattered long ago. Their survival in such orbits suggests either recent placement or long-term stabilization. Both possibilities require explanation. One explanation involves the slow influence of the galactic environment. The Sun does not exist in isolation. It moves through the Milky Way, experiencing tidal forces and occasional stellar flybys. These interactions can reshape distant orbits subtly, but cumulatively. Modelling these effects is complex, and small changes in assumptions produce different outcomes. Another explanation involves the collective gravity of the Kuiper belt itself. While individual objects are small, their combined mass may exert more influence than previously estimated. This mass distribution is still being refined. Infrared surveys and stellar occultations continue to update estimates. The distant massive object hypothesis remains compelling because it simplifies the problem. One influence can account for multiple features. Simplicity, however, is not proof. Nature does not always choose the simplest explanation. It chooses the one that fits. NASA's silence on definitive explanation reflects this ambiguity. The agency does not claim to know more than the data allows. It does not fill gaps with speculation. It waits. This waiting is often misinterpreted. In public discourse, unexplained data invites suspicion. The assumption emerges that explanation exists but is withheld. This assumption misunderstands how explanation functions in science. Explanation is not stored, it is built. The objects at the edge behave strangely only in relation to expectations formed with incomplete information. As more data accumulates, strangeness often dissolves. What once seemed aligned becomes dispersed. What once seemed anomalous becomes typical within a broader context. NASA's long-term strategy reflects this reality. Surveys continue. New telescopes come online. Sensitivity improves. Coverage expands. Each improvement reduces uncertainty slightly. No single discovery resolves the pattern. Resolution emerges from accumulation. The outer solar system challenges human patience. Its timescales exceed institutional cycles. Its distances exceed intuitive scale. Patterns reveal themselves only to those willing to wait across generations of observation. NASA operates within this temporal framework, even as public interest moves faster. The idea that certain data did not fit does not imply that something was wrong. It implies that something was incomplete. Incompleteness is the natural state of frontier science. It does not demand dramatic answers. It demands careful extension of inquiry. As attention continues, the focus will move toward how long confirmation takes, why certain hypotheses remain unresolved for decades, and why restraint is often mistaken for evasion. The strange behavior at the edge is not a signal of hidden knowledge, but a reminder that the solar system is larger, slower, and more complex than early models allowed. The data does not resist explanation because it conceals something. It resists because explanation has not yet caught up, and in that delay stories arise to fill the silence. In astronomy, time is not just a subject of study. It is a constraint, a tool, and often the deciding factor between speculation and certainty. Some discoveries arrive quickly, announced within months of detection. Others unfold so slowly that entire careers pass before conclusions harden into acceptance. This difference is not arbitrary. It is shaped by the nature of what is being observed, the distance involved, and the discipline required to separate what appears plausible from what can be demonstrated beyond reasonable doubt. Objects in the outer solar system exist on timescales that dwarf human rhythms. Their orbits stretch across centuries or millennia. Their motion against the background of stars is subtle, almost reluctant. Detecting them once is rarely enough. Detecting them twice may still mean very little. To know what an object is, where it came from, and how it behaves, astronomers must watch it long enough for its motion to reveal itself clearly. This requirement alone explains why patience is built into the structure of discovery. Verification begins with repetition. A single observation can be a fluke. A second can be coincidence. Only repeated detection, under different conditions, using different instruments, begins to establish reality. For nearby asteroids, this process can be rapid. Motion is obvious. Orbits close quickly. For distant objects, repetition may take years. Sometimes the object moves so slowly that its position barely changes relative to background stars over an entire observing season. This creates an immediate problem. Without clear motion, distance cannot be established confidently. Without distance, size and mass remain uncertain. An object that appears faint could be small and close, or large and distant. Infrared signatures complicate this further. Heat emission depends on size, composition, and temperature. A cold, large object far away can resemble a warm, smaller object closer in. Distinguishing between these possibilities requires additional data, often gathered over long intervals. Orbit determination is where time exerts its greatest influence. An orbit is not a snapshot. It is a curve traced through space over time. To calculate it accurately, astronomers need to observe an object across a meaningful fraction of its path. For planets with orbital periods measured in tens of thousands of years, this fraction is vanishingly small within a human lifetime. Early orbital estimates are therefore provisional, subject to revision as more data arrives. NASA and the broader astronomical community treat these early estimates with caution for a reason. An incorrect orbit propagates error forward. It leads to false predictions, misclassification, and wasted observational effort. The cost of announcing a discovery prematurely is not embarrassment. It is confusion that takes years to correct. This is why confirmation standards are strict. Before an object is declared new, its existence must be confirmed independently. Its motion must be consistent with gravitational laws. Its observations must align across instruments. This process is not slowed by reluctance to share. It is slowed by the need to be right. The history of astronomy is filled with examples of caution rewarded. Neptune's discovery succeeded because predictions were precise and repeatable. Pluto's discovery, while real, illustrated the danger of expectation. For decades, its role was misunderstood because its mass was assumed rather than measured accurately. That assumption shaped interpretation long after data suggested otherwise. NASA learned from this history. Modern discovery protocols are deliberately conservative. The agency does not rush to name objects whose properties are still underdetermined. It does not frame hypotheses as findings. It separates detection from explanation, allowing each to mature at its own pace. Scientific caution is often mistaken for secrecy because it lacks narrative closure. When an object is detected but not announced as significant, it can appear as though something is being withheld. In reality, it is being tested. The difference between withholding and verifying is invisible from the outside. Inside the process, it is everything. Verification also depends on elimination. Many candidates do not survive scrutiny. A detection might later be identified as a background galaxy. A heat signature might resolve into instrumental noise. A moving object might turn out to be a known asteroid observed under unusual conditions. Each elimination refines understanding, even though it produces no headline. NASA's surveys generate far more false positives than confirmed discoveries. This is expected. Sensitivity increases detection, but also noise. Filtering that noise requires discipline. Only objects that persist through multiple layers of verification are retained. This filtration is slow by design. Orbits add another layer of complexity because they are influenced by more than one body. The outer solar system is not isolated from the galaxy. Galactic tides exert subtle forces. Passing stars disturb distant objects. Even the collective mass of small bodies can alter trajectories over long timescales. Modelling these influences requires assumptions that must be tested against observation. This is why hypotheses remain open for so long. When multiple explanations fit the data equally well, science does not choose the most dramatic. It waits for additional constraints. Additional constraints often arrive only after years of observation. NASA's communication reflects this internal process. Statements are framed around confidence levels rather than certainty. Language emphasizes what is known, what is likely, and what remains unclear. This language is precise but unsatisfying to those seeking definitive answers. Precision, however, is not negotiable. The verification process also involves peer review. Findings are scrutinized by independent experts who have no stake in outcome. Alternative explanations are proposed. Assumptions are challenged. Models are stress-tested. This process is slow and sometimes adversarial, but it is essential. It prevents consensus from forming around error. Time also plays a role in cultural memory. A hypothesis proposed today may persist in public imagination, even after being quietly discarded by science years later. Corrections rarely travel as far as speculation. NASA cannot control this asymmetry. It can only continue refining its work. In the case of distant objects, decades-long verification is not exceptional. It is normal. The outer solar system reveals itself on scales that resist urgency. Expecting rapid confirmation, there is like expecting continental drift to be visible in real time. Scientific caution exists not to suppress discovery, but to protect it. Each confirmed object becomes part of a shared framework. Errors propagate widely. Carelessness undermines trust. NASA's restraint is therefore an investment, not a liability. As observation continues and instruments improve, uncertainty narrows. Hypotheses that cannot survive constraint are abandoned. Others gain support gradually. The timeline is measured not in press cycles but in orbital arcs. Understanding why some discoveries take decades requires adjusting expectations. The universe does not operate on human schedules. Verification respects that reality. It honors the scale of what is being studied rather than forcing it into premature clarity. As attention moves forward, the next layer involves how silence and speculation interact in the absence of resolution, and why unanswered questions often say more about patience than about concealment. In earlier centuries, the space between discovery and explanation was occupied by distance and time. Letters took weeks to travel. Papers circulated slowly. Debate unfolded across years rather than hours. Silence when it occurred was rarely noticed because information itself moved at a measured pace. The internet changed this dynamic completely. It collapsed distance, accelerated interpretation, and transformed gaps in knowledge into spaces that demand immediate filling. In this environment, silence does not remain neutral, it becomes suggestive. NASA operates on timelines shaped by verification and review. The internet operates on timelines shaped by attention. When these two rhythms collide, misunderstanding becomes almost inevitable. A delay that feels routine inside a scientific institution can feel conspicuous outside it. A lack of comment that reflects uncertainty can be interpreted as avoidance. The difference lies not in intent, but in expectation. The modern information ecosystem rewards speed over accuracy. Interpretation often precedes evidence. In this context, data released without narrative framing invites improvisation. Raw data sets, technical catalogues, and provisional findings are accessible to anyone with an internet connection. This accessibility is unprecedented and valuable, but it also removes layers of mediation that once provided context. When NASA releases a catalogue of detected objects, it does so with annotations, uncertainty ranges, and methodological notes. These details are essential for interpretation, but easy to overlook. Outside the scientific community, they are often stripped away. What remains are lists of objects labelled unknown, unconfirmed, or provisional. These labels, intended as technical descriptors, take on narrative weight. Silence enters when follow-up does not occur publicly or immediately. An object flagged as ambiguous may later be resolved quietly, reclassified as noise or a known phenomenon. That resolution might appear only in an updated database, or a technical paper read by specialists. It does not always generate a press release. To those tracking the initial ambiguity, the absence of a public update feels unresolved. The object becomes a loose end. Loose ends invite stories. The internet excels at story generation. Forums, videos, and articles reinterpret fragments of information, weaving them into coherent narratives that satisfy emotional and cognitive needs. These narratives often outpace the slower corrective mechanisms of science. Once established, they become resilient. The story of Nibiru illustrates this process clearly. NASA's statements denying the existence of a threatening rogue planet were direct and repeated. What NASA did not do was narrate every step of its ongoing observation process in accessible terms. This left room for reinterpretation. Denial addressed the conclusion. It did not address the process. The process, opaque by nature, became the focus of suspicion. In the internet age, absence of explanation is often treated as explanation withheld. This assumption reverses the logic of scientific caution. Instead of seeing silence as uncertainty, it is seen as concealment. The faster information moves, the less tolerance there is for waiting. Speculation thrives in this environment because it offers immediacy. It provides closure where science offers openness. A speculative explanation may be wrong, but it feels complete. It replaces uncertainty with structure. Humans are naturally drawn to structure. Algorithms amplify this tendency. Content that provokes emotion spreads more widely than content that emphasizes restraint. Speculative narratives about hidden planets, suppressed knowledge, or impending revelation generate engagement. Technical explanations about orbital modelling and error margins do not. Over time, the balance of visibility shifts. NASA's communication style does not adapt easily to this landscape. Its language is careful, measured, and technical. It does not frame uncertainty as intrigue. It does not dramatize the unknown. This consistency preserves credibility within science, but limits reach in popular discourse. The result is a perception gap. Within the scientific community, silence often means work continues. Outside it, silence suggests something is being avoided. This gap widens when speculation fills the space faster than correction can follow. Correction itself faces obstacles. When NASA addresses speculation directly, it often does so with factual rebuttal. Facts, however, do not displace narratives easily. Once a story has formed, new information is filtered through it. Denial becomes confirmation of resistance. Explanation becomes misdirection. The internet also flattens authority. Expertise competes with opinion on equal footing. A detailed paper and a persuasive video appear side by side in search results. The criteria for trust shift from credentials to coherence. A story that feels internally consistent can outweigh one that is externally validated. Gaps in data become fertile ground in this environment. The outer solar system contains many such gaps. Objects are distant, orbits are incomplete, detection limits exist. Each limitation can be reframed as secrecy rather than constraint. The distinction requires patience to appreciate. NASA does not narrate every unknown because unknowns are numerous. Most resolve quietly. Announcing each would create noise rather than clarity. The selective communication strategy is rational within science but counterintuitive online. What is omitted becomes significant by default. Speculation also benefits from temporal asymmetry. Predictions can be made quickly. Disproof takes time. When predictions fail, narratives adjust rather than dissolve. Dates shift. Mechanisms change. The core belief remains intact because it is no longer anchored to specific claims. It becomes adaptive. NASA's statements, by contrast, are static. They change only when evidence changes. This rigidity, essential for accuracy, can appear unresponsive in a fast-moving discourse. The same denial repeated over years may be interpreted not as consistency, but as evasion. Silence is also shaped by institutional boundaries. NASA does not speculate publicly beyond evidence. It does not comment on hypothetical constructs framed outside scientific methodology. This restraint is misread as avoidance when speculation dominates conversation. The internet age blurs the line between question and accusation. Asking why NASA does not explain something often carries an implicit assumption that explanation exists. This assumption shifts burden unfairly. Science does not explain what it does not know. It investigates. Stories formed in gaps often incorporate fragments of truth. Infrared surveys exist. Objects at the edge behave unexpectedly. Verification takes decades. These facts are real. When arranged selectively, they support narratives that diverge from scientific interpretation while retaining plausibility. NASA's challenge is structural. It operates within a framework that values uncertainty as honesty. The internet values certainty as engagement. Bridging this divide is difficult without compromising one side. Understanding how gaps become stories requires recognizing that silence is interpreted differently depending on context. Within science, silence often marks a space still under examination. Within narrative culture, silence invites meaning. As observation continues and data accumulates, some gaps will close. Others will remain, not because of concealment, but because of scale. The outer solar system will not yield all its secrets quickly. This prolonged openness will continue to generate stories. The question is not whether speculation will exist. It will. The question is how it interacts with evidence over time. Sometimes speculation collapses under weight of data. Sometimes it adapts and persists independently. NASA does not control this process. It can only continue observing, publishing, and refining. Silence, in this context, is not absence of knowledge, but absence of premature conclusion. As attention moves forward, the focus turns to what NASA has explicitly denied, what it has chosen not to elaborate on, and how those choices are interpreted. The distinction between denial and avoidance becomes central, because it is in that distinction that trust either stabilizes or erodes. NASA's public denials around Nibiru and similar ideas are among the most direct statements the agency has ever made in response to popular speculation. They are clear, repetitive, and unambiguous in one specific area. There is no large, undiscovered planet moving through the inner solar system on a trajectory that threatens Earth. There is no object approaching on a hidden schedule. There is no imminent celestial disruption being concealed from the public. These denials are not hedged. They are not conditional. They are firm because the evidence required to contradict them would be overwhelming and unmistakable. A planet-sized body entering the inner solar system would announce itself loudly. Its gravitational influence would distort the orbits of known planets in ways that could not be missed. Its infrared signature would be detected across multiple surveys. Its motion would be tracked independently by observatories around the world, many of which operate outside NASA's control. None of this has occurred. NASA's denial rests not on absence of curiosity, but on abundance of constraint. What NASA denies, it denies completely. What it does not deny is more subtle, and this subtlety is often mistaken for evasion. NASA does not deny that the outer solar system is incompletely mapped. It does not deny that distant objects exist beyond Neptune, whose orbits are not yet fully understood. It does not deny that current models are provisional, or that future discoveries may revise them. These are not denials because they are not claims to be rejected. They are acknowledgements of limitation. The distinction matters. Denial addresses specific assertions. Explanation addresses process. NASA denies the narrative of a dangerous hidden planet. It avoids turning process into spectacle. This avoidance is not strategic silence, it is methodological discipline. NASA's public-facing communication tends to operate at the level of conclusion rather than deliberation. This is not unique to space science. Medical agencies announce approved treatments, not every failed trial. Weather agencies announce forecasts, not every discarded model. The internal process remains largely invisible, unless one seeks it out deliberately. In the Internet age, invisibility is often interpreted as intentional concealment. NASA avoids explaining certain things not because they are secret, but because they are unresolved. Unresolved does not mean mysterious. It means insufficiently constrained. Explaining such matters prematurely would create false certainty. False certainty, once established, is difficult to retract. One example lies in orbital clustering at the edge of the solar system. NASA has acknowledged the observations. It has discussed proposed explanations. It has supported further study. What it has avoided is presenting any single explanation as definitive. This restraint frustrates those accustomed to narrative closure. It is also what makes scientific conclusions durable. Another area often cited involves infrared detections that were later reclassified or not followed publicly. NASA avoids narrating these cases because most resolve into mundane explanations. To explain each one would require explaining the nature of noise, error margins, detector behavior, and statistical filtering repeatedly. This is not avoidance. It is prioritization. NASA also avoids speculating about hypothetical objects framed outside established methodology. When questions are posed using language drawn from myth, prophecy, or non-scientific reinterpretation, NASA does not engage on those terms. This refusal is sometimes framed as fear of discussion. In reality, it reflects a refusal to legitimize frameworks that cannot be tested or constrained. Avoidance in this sense is boundary maintenance. Science operates within defined rules. Those rules exist to protect reliability. When a claim cannot be falsified, science does not debate it. It waits for evidence that can be measured. NASA's denials are often accused of being too narrow. Critics argue that the agency denies specific scenarios while leaving others unaddressed. This criticism misunderstands how claims are evaluated. NASA addresses claims that intersect with observable reality. It does not address hypothetical constructs that shift definition to avoid disproof. For example, the idea that a planet exists but is hidden through advanced technology, dimensional displacement, or intentional cloaking is not denied explicitly. Not because it is possible, but because it is not testable. Denial applies only where evidence could exist. Avoidance applies where evidence cannot. This difference is uncomfortable for those seeking reassurance. It can feel like evasion. It is not. It is epistemological discipline. NASA cannot explain what cannot be investigated. Another area of avoidance involves long-term uncertainty. NASA does not provide definitive answers about the total number of objects in the outer solar system, the exact mass distribution of the Kuiper belt, or the detailed structure of the Oort cloud. These are active research areas. Explaining them as settled would be inaccurate. Avoiding definitive explanation is therefore an act of honesty. The problem arises when avoidance is interpreted through a lens shaped by distrust. In such a lens, silence becomes strategy, restraint becomes deflection, consistency becomes rehearsed denial. The same behaviour that signals integrity within science signals suspicion outside it. NASA's institutional culture reinforces this gap. Scientists are trained to speak cautiously, to emphasise uncertainty, to avoid overstating conclusions. Public discourse often rewards the opposite. This mismatch creates the impression that something is being held back when, in fact, nothing has yet been established firmly enough to share. NASA has also avoided engaging emotionally with speculation. Its statements are factual, not persuasive. They do not attempt to convince through rhetoric. They present information and expect it to stand on its own. In a media environment driven by narrative and emotion, this approach feels inadequate. What NASA has denied consistently is intent. There is no intention to conceal planetary threats. There is no intention to suppress discovery. There is no intention to mislead. These denials are backed by institutional structure. Data is shared internationally. Discoveries are made by distributed teams. Secrecy on the scale imagined by speculation would require coordination beyond plausibility. What NASA avoids explaining in popular terms is how incomplete knowledge actually works. It avoids saying, repeatedly and explicitly, that not knowing yet is not the same as knowing and hiding. This distinction is foundational within science but counterintuitive outside it. The avoidance also protects against misinterpretation. When agencies explain uncertainty, that explanation is often selectively quoted or reframed to support speculation. Silence, paradoxically, reduces the material available for distortion. This does not eliminate speculation, but it limits institutional participation in it. NASA's careful avoidance extends to naming. Names carry implication. To name a hypothetical object is to grant it provisional existence. NASA refrains from adopting names rooted in mythology or popular narrative precisely because doing so would blur boundaries. Planet 9 remains a placeholder because it remains hypothetical. This restraint mirrors the earlier history of Planet X learned the hard way. The agency's behaviour is shaped by institutional memory. Past experiences where premature conclusions created long-lasting misconceptions have left a mark. Pluto's reclassification, for example, demonstrated how difficult it is to correct public understanding once a narrative is settled. NASA learned to move more slowly, not to deceive, but to avoid misalignment between evidence and expectation. What NASA has been denied openly. What it has avoided explaining has been avoided consistently. The pattern is not selective silence, it is uniform restraint. Where evidence exists, it is shared. Where it does not, speculation is not entertained. This does not satisfy those who expect institutions to fill every gap with explanation. It was never designed to. Science advances by narrowing uncertainty, not erasing it prematurely. The outer solar system remains a frontier precisely because it resists full explanation. Understanding this distinction reframes NASA's silence. It is not the silence of concealment. It is the silence of unfinished work. That silence persists not because answers are hidden, but because they are still forming. As observation continues, some explanations will solidify, others will collapse. NASA's denials may remain unchanged while its understanding deepens. This stability can appear suspicious only if one assumes that all knowledge arrives fully formed. The next layer of this story moves beyond denial and avoidance into comparison. It examines how similar questions are treated across astronomy, why hypothetical objects are common at the edge of knowledge, and how Planet 9 fits into a broader pattern, rather than standing as an exception. Between what is firmly known and what is entirely speculative lies a wide and uncomfortable space. It is a space science occupies constantly, though it rarely advertises the fact. This is where Planet 9 and brown dwarfs exist conceptually, not as discoveries, but as possibilities constrained by evidence, shaped by limits, and disciplined by what has already been ruled out. Understanding this space is essential, because it is precisely where confusion most often arises. Planet 9 did not appear as a rumour. It emerged as a mathematical response to a pattern. Certain distant objects in the outer solar system exhibited orbital characteristics that resisted easy explanation. Their paths appeared clustered in orientation, as if shepherded by a distant gravitational influence. This observation did not demand a new planet. It allowed one. Allowing is not the same as asserting. That distinction is subtle, but it defines the difference between hypothesis and myth. The proposed Planet 9 is not a revision of older ideas about Planet X. It shares a naming lineage only in the loosest sense. Its predicted properties are radically different from anything associated with catastrophic narratives. It would be far from the Sun, likely hundreds of astronomical units away. Its orbit would be long, slow, and stable, taking thousands of years to complete a single revolution. It would not cross the paths of known planets. It would not approach Earth. Its influence would be quiet, cumulative, and detectable only through long-term statistical effects. NASA has treated this hypothesis with measured interest. It has acknowledged the modelling. It has supported observational efforts designed to test it. What it has not done is present Planet 9 as an established object. This restraint reflects the current state of evidence. The hypothesis fits some data well. It does not yet fit all data conclusively. Alternative explanations remain viable. Brown dwarfs occupy a different conceptual space. They are not hypothetical. They are known objects, observed and catalogued in large numbers throughout the galaxy. They form like stars but lack sufficient mass to sustain hydrogen fusion. They glow faintly in infrared wavelengths and cool slowly over time. Because of their low luminosity, they are difficult to detect, especially at great distances. The existence of brown dwarfs naturally raises questions about whether one could exist closer to the Sun than currently known. This possibility has been examined extensively. Infrared surveys conducted by NASA and other agencies have placed strong limits on such scenarios. Objects of brown dwarf mass within a certain distance would have been detected by now. Their absence is not assumed, it is demonstrated. This is where the space between certainty and possibility narrows. While it is possible that a distant planet exists far beyond Neptune, it is extremely unlikely that a brown dwarf companion to the Sun exists undetected within the surveyed volume. The difference lies in detectability. Brown dwarfs emit significantly more infrared radiation than planets. They are easier to find. The fact that surveys have not found one near the Sun is meaningful. Planet 9, by contrast, would be much colder and less luminous. Its infrared signature would be faint. Its reflected light negligible. Its detection would require targeted searches guided by modelling. This difficulty keeps the hypothesis alive without elevating it to certainty. NASA's role in navigating this space is constrained by evidence. It cannot collapse possibility into fact prematurely. It also cannot dismiss possibility without adequate constraint. The agency therefore operates in a zone of conditional language. Words like could, may, and consistent with dominate communication. This language is precise but unsatisfying. The public often treats this conditional space as suspicious. If something is possible but unconfirmed, it feels unresolved. Unresolved feels unstable. Stability is sought through narrative, not probability. This is where Planet 9 is sometimes conflated with older ideas about hidden worlds. The distinction between possibility and certainty is flattened. Brown dwarfs illustrate why this flattening is misleading. Once hypothetical, they are now well understood. Their properties are constrained. Their population is mapped statistically. Their absence near the sun is established with confidence. The process that led to this certainty was slow, methodical, and grounded in survey science. Planet 9, if it exists, is earlier in this process. NASA's silence on definitive claims reflects this difference in maturity. Brown dwarfs moved from possibility to certainty because evidence accumulated. Planet 9 remains provisional because evidence is still sparse. The agency's behavior is consistent across both cases. Another source of confusion arises from scale. People often imagine hidden objects as singular, dramatic presences. In reality, the outer solar system is shaped by collective effects. Many small bodies exert influence. The galactic environment contributes. Stellar encounters leave imprints. A single explanation is appealing but not always necessary. NASA's modelling efforts account for this complexity. Simulations test multiple scenarios. Some reproduce observed clustering without invoking a new planet. Others require one. The results depend on assumptions about initial conditions, mass distribution, and external forces. This sensitivity reinforces caution. The space between certainty and possibility is not empty. It is actively explored. Observational campaigns continue. New telescopes extend sensitivity. Each improvement constrains hypotheses further. Some possibilities shrink, others persist. None leap directly to confirmation. NASA avoids framing this process as a countdown to discovery. There is no guarantee that Planet 9 will be found. There is also no guarantee that it does not exist. Science tolerates this ambiguity because it reflects reality. The universe does not owe resolution on human timelines. Brown dwarfs serve as a reminder that not all possibilities remain open indefinitely. Once surveys reach sufficient depth, some questions close. The question of a nearby stellar mass companion to the Sun is effectively closed. The question of a distant planetary mass object remains open. This distinction undermines claims that NASA selectively acknowledges what suits it. The agency follows evidence where it leads. When evidence closes doors, it accepts closure. When evidence leaves doors ajar, it waits. The emotional discomfort with waiting drives speculation. The internet amplifies that discomfort. Possibility becomes probability. Probability becomes expectation. Expectation becomes belief. NASA does not participate in this escalation. It remains anchored to constraint. Planet 9 occupies a narrow corridor. It is neither fantasy nor fact. It is a working idea subject to elimination. Brown dwarfs once occupied a similar corridor. They moved out of it through accumulation of evidence. Planet 9 may follow or it may dissolve. NASA's knowledge sits comfortably within this framework. It knows what surveys have ruled out. It knows what remains plausible. It knows what data suggests and what it does not. What it does not do is convert plausibility into promise. The space between certainty and possibility is often mistaken for secrecy because it lacks narrative clarity. In truth, it is the most honest place science can occupy when evidence is incomplete. Pretending otherwise would undermine trust far more than restraint ever could. As observation continues, this space will change shape. Some possibilities will collapse under constraint. Others will sharpen into discovery. The transition will be gradual, not dramatic. It will be marked by papers, revisions, and quiet consensus, rather than revelation. Understanding this space reframes how NASA's silence should be read. Silence here is not withholding. It is the sound of probability being refined. The next layer of this story shifts focus again, away from objects themselves and toward interpretation. It examines how belief and skepticism interact with this uncertain terrain. and why the divide between them persists even as data improves. If something is out there, truly out there, beyond Neptune and beyond the familiar architecture of the solar system, its significance would not lie in danger or disruption, but in context. It would not rewrite daily life or alter the sky overnight. Its meaning would be quieter, deeper, and far more structural. It would change how the solar system is understood, not how it is feared. The modern picture of the solar system is already different from the one taught a generation ago. It is no longer a tidy sequence of planets fading neatly into empty space. It is a layered system, rich with debris, shaped by migration, collision, and long-term gravitational negotiation. The discovery of something substantial in the outer reaches would not overturn this picture. It would complete a part of it that is currently sketched in pencil rather than ink. A distant planetary body would first and foremost be a historical witness. Its orbit, composition, and position would preserve information about the early solar system that inner planets have long since erased. Close to the Sun, geological activity, impacts, and thermal evolution have rewritten surfaces repeatedly. Far from the Sun, change happens slowly. Objects there retain memory. If a large body exists in that region, it would be a fossil of formation, carrying clues about how material was distributed, how planets migrated, and how the Sun interacted with its birth environment. One of the most profound implications would involve planetary migration. Current models suggest that the giant planets did not form exactly where they are now. They moved subtly but decisively, reshaping the solar system as they went. This movement scattered smaller bodies outward and inward, populating the Kuiper Belt and beyond. A distant planet could be a survivor of this process, either a remnant that avoided ejection or an object captured during the Sun's early life in a dense stellar nursery. Such a discovery would strengthen the idea that planetary systems are dynamic rather than static. It would align the solar system more closely with exoplanetary systems observed elsewhere, many of which show evidence of migration, eccentric orbits, and distant massive companions. Far from making the solar system unusual, it would make it more typical. The gravitational influence of a distant object would also clarify long-standing puzzles. Orbital clustering among extreme trans-Neptunian objects would gain a coherent explanation. Long-term stability models would improve. Predictions about the distribution of distant bodies could be tested more precisely. The outer solar system would shift from being a region of loosely constrained assumptions to one of structured understanding. Importantly, such an object would not imply threat. Its orbit would be stable on timescales that dwarf human history. It would not approach the inner planets. It would not perturb Earth in any meaningful way. Its effects would be measured in millimeters of orbital shift over centuries, not in dramatic encounters. The cultural reaction, however, would likely be outsized. A new planet carries symbolic weight. It reopens childhood diagrams. It invites renaming, reclassification, and debate. It challenges the feeling of completion that comes from believing the solar system is fully known. That discomfort often expresses itself as anxiety, but anxiety is a psychological response, not an astronomical one. NASA and the scientific community would treat such a discovery methodically. Confirmation would come first. Independent verification would follow. Orbital parameters would be refined slowly. Naming would be cautious. There would be no rush to narrative. The process would take years, not because information is withheld, but because precision accumulates gradually. There would also be implications for how distant regions are searched. A confirmed object would focus future surveys, guiding telescopes toward resonant regions and predicted orbital pathways. The discovery would not end exploration. It would sharpen it. The unknown would become more constrained, not eliminated. Another consequence would involve classification itself. The debate over what constitutes a planet would resurface, but with new nuance. Pluto's reclassification demonstrated that definitions evolve alongside understanding. A distant object would test those definitions again, not because it demands exception, but because it forces clarity. Classification is not about status, it is about consistency. From a scientific perspective, the most important change would be philosophical. It would reinforce the idea that absence of evidence is not evidence of absence, but that evidence eventually resolves absence when patience is applied correctly. It would validate survey science, long-term observation, and restraint. It would also challenge sensational narratives by contrast. The reality of discovery is anticlimactic compared to myth. There would be no sudden realization that something had been hidden all along. The data trail would be public, traceable, and incremental. The story would be one of persistence, not revelation. If something is out there, it would not vindicate claims of secrecy. It would demonstrate the opposite. It would show that large-scale observation, distributed verification, and methodological caution work as intended. It would show that the universe yields its structure slowly, not because it resists knowledge, but because it is vast. The solar system would feel slightly larger, slightly older, slightly more complex. That complexity would not demand fear. It would invite humility. The sense that everything important has already been discovered would weaken, replaced by the recognition that exploration is ongoing. There would also be a subtle shift in how humanity sees its place. Discoveries at the edge remind us that familiarity is local. Our sense of cosmic neighbourhood is shaped by detection limits rather than reality. Each expansion of understanding moves the boundary outward, not because the universe changes, but because our perception improves. In the long term, such a discovery would likely fade into normalcy. Textbooks would update, diagrams would adjust. Students would grow up with a revised picture that feels complete until it too proves provisional. This cycle is not failure, it is progress. If nothing is out there, that outcome is equally meaningful. It would imply that current models require revision in other directions. It would elevate alternative explanations. It would refine understanding of collective dynamics and galactic influence. Absence, when established rigorously, is as informative as presence. NASA's role in either outcome remains the same. Observe, constrain, publish. Avoid overstating conclusions. The agency does not prepare for revelation. It prepares for refinement. The idea that discovery must justify anticipation misunderstands science. Discovery justifies itself by improving coherence. Whether a distant object exists or not, the process of searching already enhances understanding. Each survey maps more of the unknown. Each null result narrows possibility. If something is out there, it will not arrive as a surprise. It will arrive as the endpoint of years of incremental narrowing, recognized quietly at first, then accepted gradually. By the time it is announced, it will already be familiar to those who followed the data. The solar system will not feel suddenly dangerous or incomplete. It will feel more honest, less imagined, more precisely described. As attention moves toward the final layers of this story, the focus turns inward again, to how people respond to uncertainty, how belief and skepticism form around incomplete knowledge, and why the same data can produce radically different interpretations depending on expectation. The existence or non-existence of something out there matters less than how that possibility is handled while it remains unresolved. At the edges of uncertainty, where evidence is incomplete and conclusions remain provisional, people tend to sort themselves into opposing camps. On one side stand the skeptics, armed with caution, probability, and a strong preference for explanations that require the fewest new assumptions. On the other side stand the believers, driven by pattern recognition, narrative coherence, and the conviction that absence of confirmation is not confirmation of absence. Between them lies a much quieter space, one that rarely attracts attention and almost never generates headlines. This is the middle ground where astronomy actually lives. Skepticism, in its scientific form, is not disbelief. It is discipline. Skeptics do not deny possibilities. They resist commitment until constraint justifies it. Their posture is not hostile, but reserved. In astronomy, skepticism is less about saying no and more about saying not yet. It is shaped by history, by lessons learned from premature conclusions that lingered long after they were corrected. The story of Planet X is instructive here. Early confidence persisted for decades because it felt reasonable, even elegant. Only later did improved data dissolve the need for it. Skeptics remember this. They remember how easily expectation can harden into assumption. Their caution is not cynicism, it is memory. Believers, by contrast, are not simply gullible or careless. Many are deeply engaged, well-read, and genuinely curious. Their orientation toward possibility is expansive rather than restrictive. They're comfortable holding ideas open long after institutions have grown impatient with them. Where skeptics see gaps as unresolved, believers see them as meaningful. This difference is psychological as much as intellectual. Belief thrives on coherence. When fragments of data align loosely, belief supplies connective tissue. It constructs a story that feels complete, even when evidence is partial. This does not happen because believers reject science, but because science often withholds narrative. In the absence of explanation, belief steps in. The tension between these positions is often framed as conflict, but this framing obscures something important. Both skepticism and belief arise from the same impulse, the desire to make sense of the unknown. They diverge not in curiosity, but in tolerance for uncertainty. The middle ground is occupied by working astronomers, data analysts and theorists who live with uncertainty daily. For them, ambiguity is not a threat, it is a condition. They do not feel pressure to resolve every question immediately because resolution is rarely immediate. Their confidence lies not in answers, but in method. This middle ground does not speak loudly. It does not announce certainty or mystery. It publishes incremental findings, caveated conclusions, and revised models. It acknowledges that some ideas may persist unresolved for decades without implying failure. This restraint is often misread as indecision. In reality, it is stability. In public discourse, however, this quiet space is easily overlooked. Skeptics are visible because they negate. Believers are visible because they affirm. The middle ground simply continues working. Its output is cumulative rather than declarative. It does not offer emotional satisfaction. It offers coherence over time. NASA operates squarely within this middle ground. Its statements reflect neither belief nor dismissal, but constraint. When it denies catastrophic scenarios, it does so decisively. When it addresses unresolved questions, it does so cautiously. This dual posture confuses audiences accustomed to binary positions. For skeptics outside the scientific community, NASA's caution can feel excessive. If something is not proven, they argue, it should be dismissed. For believers, the same caution feels evasive. If something is not dismissed, they argue, it must be meaningful. Both interpretations flatten nuance. The quiet middle ground recognizes that meaning and proof operate on different axes. Something can be meaningful to explore without being proven. Something can be unproven without being implausible. This is not indecision, it is calibration. Astronomy provides many examples of ideas that lived in this space for long periods. The existence of exoplanets was once speculative. Gravitational waves were predicted long before they were detected. The Kuiper Belt itself was hypothetical for decades. In each case, believers were early, skeptics were cautious, and the middle ground kept refining tools until evidence resolved the question. Importantly, resolution did not validate belief wholesale or skepticism absolutely. It validated method. Some early ideas were confirmed, others were revised or discarded. What persisted was not a camp, but a process. In the case of distant objects beyond Neptune, this process remains active. Skeptics emphasize survey limits and alternative explanations. Believers emphasize patterns and persistence. The middle ground examines both, modelling scenarios, expanding datasets, and refining assumptions. It does not require alignment with either camp to function. The internet complicates this balance. Visibility favours extremes. Nuance does not travel well. A statement that says, "This is interesting but unresolved," generates less engagement than one that says, "This proves everything," or "This proves nothing." As a result, the middle ground is underrepresented in popular understanding. This absence reinforces polarization. Skeptics become more dismissive. Believers become more entrenched. Each side sees the other as unreasonable. Meanwhile, the actual work continues unaffected by this dynamic. NASA does not attempt to mediate this cultural divide. It cannot. Its mandate is not persuasion, but observation. It provides data and interpretation within defined limits. How that information is received lies outside its control. The persistence of belief in ideas like Nibiru does not indicate failure of science. It indicates that science does not fulfill all psychological needs. It does not provide certainty on demand. It does not offer narrative closure when evidence is incomplete. This restraint creates space for alternative meaning-making. The challenge arises when belief and skepticism stop interacting with evidence. When belief becomes immune to disproof, it detaches from inquiry. When skepticism becomes reflexive dismissal, it closes prematurely. The middle ground resists both tendencies by remaining responsive to data. Astronomy by nature requires this responsiveness. The universe does not conform to expectation. Models must adapt. Confidence must remain provisional. The quiet middle ground is not a compromise between belief and skepticism. It is a different posture entirely. It accepts that uncertainty can persist without being pathological. It accepts that some questions may remain open longer than a human lifetime. It accepts that curiosity does not require immediate resolution. In this space, questions about distant objects are not framed as threats or revelations. They are framed as opportunities to refine understanding. The emotional charge drains away. What remains is structure. For those outside this space, this can feel unsatisfying. The desire for definitive answers is strong. The desire to know whether something is out there or not feels urgent. The middle ground does not respond to urgency. It responds to constraint. This difference explains why debates around hidden worlds often stall. They are not debates about data. They are debates about how uncertainty should feel. Skeptics prefer closure through negation. Believers prefer openness through affirmation. Astronomy prefers openness through patience. The quiet middle ground does not ask others to abandon their positions. It simply continues working regardless of them. Over time, evidence accumulates, patterns sharpen or dissolve, possibilities narrow. Eventually, some questions resolve. When resolution arrives, it rarely looks like victory for one side. It looks like revision. It looks like updated diagrams, adjusted models, and a new baseline of understanding. The emotional investment dissipates. The question becomes background knowledge. Until then, the middle ground remains. It is not empty, it is active. It is where most scientific understanding actually lives, even if it rarely receives attention. As this exploration nears its close, attention turns away from debate and back toward perspective. What remains is not a verdict, but a way of holding uncertainty that does not require conflict. The final movement reflects on why some mysteries persist, not because they resist explanation, but because they are approached best when urgency fades and curiosity is allowed to soften rather than demand resolution. Hidden worlds have always lived comfortably in the human mind, long before telescopes, equations, or space agencies existed. They appear in stories because they satisfy something quiet and persistent, a sense that reality is larger than what is immediately visible, that the edges of knowledge are not walls but horizons. This idea does not require proof to feel meaningful. It requires only the recognition that experience is partial, that what is known has always emerged slowly from what was once unseen. Astronomy, perhaps more than any other science, lives in constant conversation with this instinct. The sky invites projection. Its vastness encourages imagination. For most of human history, the night above was not a map, but a mystery. Patterns were drawn where understanding had not yet arrived. Gods, omens, and destinies filled the darkness, not because they were seen, but because something had to live there. Modern science did not remove this impulse, it redirected it. Telescopes replaced mythic eyes. Mathematics replaced divine intention. Yet the structure remained familiar. Something is observed, something is inferred, something remains unresolved. The unknown persists, and with it, the quiet space where imagination settles. Hidden worlds are compelling because they sit just beyond certainty. They are close enough to feel plausible, and distant enough to resist confirmation. This balance creates a gentle tension, one that does not demand resolution but invites contemplation. A fully known universe would be tidy, but it would also be inert. Mystery gives movement to thought. The idea of a hidden planet does not endure because it threatens. It endures because it suggests incompleteness. It implies that the solar system, often presented as a finished diagram, is still being drawn. This sense of ongoing discovery mirrors human experience itself. Lives are not complete stories. They unfold, they revise, they leave loose threads. NASA's role in this narrative is often misunderstood. It is not the guardian of mystery nor its adversary. It is a participant in a long process of clarification that does not hurry itself to satisfy imagination. Its work reduces uncertainty gradually, knowing that some uncertainty will always remain. This restraint is not a denial of wonder, it is a preservation of it. The tension between what is known and what is imagined is not something to be resolved, it is something to be held. When science moves too quickly to explain everything, it risks flattening curiosity. When imagination detaches entirely from evidence, it risks drifting into illusion. The space between these extremes is where reflection becomes possible. Hidden worlds also resonate because they echo inner experience. Much of what shapes human life operates unseen. Thoughts arise without visible cause. Memories surface unexpectedly. Emotions shift without warning. The idea that something important might exist beyond immediate perception feels intuitive because it mirrors the mind itself. In this sense, a distant planet is not just an astronomical possibility. It is a metaphor for how humans relate to reality. There is always more structure beneath the surface. There are always forces at work that cannot be observed directly, but whose influence is felt. Gravity itself was once such a force, invisible, yet undeniable. The fascination persists even when explanations are offered. When science narrows possibility, imagination adapts. The object becomes colder, farther, quieter. The narrative softens rather than disappears. This is not failure, it is transformation. Curiosity does not vanish when boundaries are drawn. It reshapes itself around them. The internet age amplifies this dynamic by accelerating exposure without slowing interpretation. Information arrives faster than understanding. Data appears without context. Gaps are noticed instantly. Stories form quickly because patience has become rare. Yet beneath this acceleration, the deeper impulse remains unchanged. Humans still seek coherence. They still lean toward meaning. Astronomy does not provide meaning directly. It provides structure. Meaning emerges when structure is contemplated slowly, without urgency. This is why the most enduring scientific ideas are not those announced loudly, but those absorbed quietly over time. They settle into understanding rather than demand attention. Hidden worlds also carry a gentle reassurance. They suggest that the universe is not exhausted by what has already been found, that even now, after centuries of observation, there are still things that require waiting. This waiting is not empty. It is active. It keeps curiosity alive without demanding reward. The outer solar system in particular embodies this patience. Its objects move slowly. Their stories unfold across timescales that dwarf human urgency. To engage with them meaningfully requires letting go of immediacy. This letting go can feel calming. It places personal concerns within a broader rhythm. There is also comfort in the idea that not everything is immediately accessible. Complete transparency can feel overwhelming. Partial knowledge leaves room to breathe. The unknown becomes a place of rest rather than anxiety when it is approached without fear. This is why hidden worlds often appear in moments of reflection rather than crisis. They surface when attention drifts outward, when the mind softens its grip on certainty. They belong more to evening thought than to midday urgency. Science, at its best, aligns with this softness. It advances carefully. It resists dramatization. It values what remains unresolved as much as what has been settled. This attitude does not diminish discovery. It deepens it. NASA's careful language, often criticized for being unexciting, mirrors this philosophy. It does not rush to close stories. It allows them to remain open until evidence insists otherwise. This openness is not weakness. It is strength measured over time. Hidden worlds capture imagination not because they promise revelation, but because they invite humility. They remind us that perspective is always limited, that understanding is provisional, and that patience is a form of wisdom. The solar system does not need to hide anything intentionally to feel mysterious. Distance alone is enough. Scale alone is enough. The universe does not withhold itself out of secrecy. It reveals itself according to its own pace. This pace, when accepted, can be soothing. It removes the pressure to know everything now. It reframes curiosity as companionship rather than pursuit. One can walk alongside unanswered questions without needing to chase them. As attention drifts away from debate and toward quiet contemplation, the idea of hidden worlds loses its urgency and gains depth. It becomes less about what might be concealed and more about how much remains to be understood gradually. The mind, like the cosmos, does not resolve all patterns at once. It benefits from rest, from letting thoughts settle without forcing conclusion. In this settling, imagination does not vanish. It becomes gentler. Hidden worlds remain, not as threats, not as secrets, but as reminders that reality is layered, that seeing is not the same as knowing, that knowledge unfolds. And within that unfolding there is room for calm. There is room for wonder without alarm. There is room to rest with the awareness that the universe is larger than any single explanation, and that this largeness does not demand anything from us in return. It simply exists, moving slowly, carrying its distant objects along paths measured not in urgency, but in time.